In this lesson, we're looking at relationships between perpendicular lines. And first thing that you see in your textbook is the construction of the perpendicular bisector of a segment. So notice that when you're constructing the perpendicular bisector of a segment, your first step is to set your compass setting a little bit more than half of the length of the segment that you're bisecting, and then make an arc from one of the endpoints. And then using the same compass setting, you do the same arc from the other endpoint. Since they intersect in 2 points, I'm able to connect those 2 points and draw the line passing through them, and that would be the perpendicular bisector. If I have a point that isn't on the line and I wanted to construct a line perpendicular to it, to this line passing through this point, what I would start to do is basically the first step is you're making a segment on this line. So you're doing that by making a random arc, having your compass point at P, and it swings through L and it passes through 2 points, and they call them A and B. And then what you do is the exact same construction as you did back here. All right, since it's probably a little bit easier to make sense of the construction, if you see the construction, I'm going to do the exact same constructions I just described here on a separate sheet of paper. So you might want to follow along on your own separate sheet of paper. So if I have a segment that I want to construct the perpendicular bisector of, I take my compass and I make my compass setting a little bit more than half. And then I make this arc, and I make the exact same arc from the other end point. Has to intersect in 2 places. You need 2 points in order to draw a line through it. When I draw the line passing through these 2 points, this line L is my perpendicular bisector of segment AB. If I had a line and a point not on that line, so here's line M and point P not on M, and I want to construct the line that is through P and is perpendicular to M. I start with my compass point at P, and I want to make 2 marks on line M. So I've just made that arc. And in making this arc, what I have done is create a segment on this line. So I could call this segment AB. And now I do the exact same construction that I did back here. I'm going to construct the perpendicular bisector of segment AB. So I make this arc. I make the exact same arc from A. And when I connect these 2 points of intersection, there's my line L is perpendicular to M, passing through P. In the first reflect question, it asks us, why do we open the compass to a setting that is greater than half the length of AB? It's because if it's less, the 2 arcs won't cross. If it's exact, I would only have 1 point, and we need 2. So now we're going to kind of flashback to reflections that we talked about in Unit A and develop some properties of perpendicular bisectors. So this first property is saying that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So let me kind of put that in clearer terms. If I have a segment AB and I have the perpendicular bisector of segment AB, well, by definition, the perpendicular bisector would be forming a 90-degree angle, and this segment would be congruent to this segment. So maybe I would call this point M. Oh, that's a convenient letter to choose, since M would be the midpoint of segment AB. But not only that, any point I pick on line L, let's say I pick this random point Q, I know that QA will be congruent to QB. And that's what I mean when I say any point on this perpendicular bisector will be equidistant from the endpoints. Okay, so in example 1, they're asking us to prove that. So they're saying consider the reflection across line M, because that's the perpendicular bisector line. Then the reflection of point P across line M is also the point P, because notice if I have a point that's on the line of reflection, it stays there. Also, the reflection of A across line M is B by the definition of reflection. And therefore, PA is equal to PB because a reflection preserves distance. So in the next reflect question, they're asking us what conclusion can we make about triangle KLJ in the diagram using the perpendicular bisector theorem. So since JM is the perpendicular bisector of KL, I know that J is equidistant from L and K. So I can draw a conclusion that triangle KLJ is isosceles. Hopefully you know that term. It has at least 2 congruent sides. In this your turn example, we're using that perpendicular bisector theorem to draw some conclusions about segment lengths. So in part 4, they're saying suppose the length of ED is 16 and the length of DA is 20. What would the length of DC be? Well, notice that the 16 is a distractor. The 16 actually in this instance doesn't have anything to do with the length of DC. What does have to do with the length of DC is that since BD is the perpendicular bisector of AC, D will be equidistant from A and C. So if DA is 20, then DC is also 20. For the your turn number 5, this time they're telling me that EC is 15, that BA is 25, and they're asking me for BC. Once again, one of these values is a distractor. It's the CE value. The length of BC will be 25. And let's remember our units. And that's it. In the explain 2, they're talking about how the converse of this perpendicular bisector theorem is also true. Remember that the converse of a statement is taking an if-then sentence and flipping it around. So in order to prove this converse, we're going to do it indirectly, and we're going to use Pythagorean's theorem. Remember that we've seen Pythagorean's theorem before. We saw it when we were talking about the distance between 2 points. So remember, Pythagorean's theorem says if I have a right triangle where A and B are the legs and C is the hypotenuse, then the equation A squared plus B squared equals C squared is a true statement. So they're telling us what the converse of the perpendicular bisector theorem says. It says, if a point is equidistant from the endpoints of a segment, then we know that that point lies on the perpendicular bisector of a segment. So we're going to prove this statement indirectly. So when you are doing an indirect proof, you start the proof by assuming, notice up here, it says that in an indirect proof, you assume that the statement you are trying to prove is false. And then you go through your proving process, and eventually you reach a contradiction. Since I am trying to prove that P is on the perpendicular bisector of AB, what I'm going to start is by assuming that what I'm trying to prove is false. So I'm going to assume that P is not on line M, which is the perpendicular bisector of segment AB. So that's why they've drawn the diagram to look like this. Then, when you draw a perpendicular line from P to the line containing A and B, it intersects at a point Q, which is not the midpoint of segment AB. So PQ forms two triangles, triangle AQP and triangle BQP. Okay, so Pythagorean's theorem tells us that AQ squared plus QP squared will equal PA squared. Similarly, in this triangle on the right, BQ squared plus QP squared will equal BP squared by the Pythagorean theorem. And then it says subtract the two equations. Okay, I'm allowed to do that. And when I subtract those two equations, I end up with AQ squared minus BQ squared and PA squared minus PB squared. But I know that PA squared minus PB squared will equal 0 because PA equals PB. That was given to us. It was given to us back here. Therefore, the length of AQ squared minus the length of BQ squared would equal 0. Well, then that would have to mean that AQ squared would equal BQ squared and that AQ equals BQ. So what I've just concluded is that this segment equals this segment. But this contradicts our statement back here that Q is not the midpoint of segment AB. Therefore, our original assumption must be incorrect and P must lie on the perpendicular bisector. In this reflect question, it says that in the proof, once we know that AQ squared equals BQ squared, why can we conclude that AQ has to equal BQ? Because we can take the square root of both sides. In this your turn example, they're telling us that the length of AD is 10 inches long, BD is 6 inches long. We're trying to find the length of AC. So if this is 10 and this is 6, they're asking us for this whole segment. And so we're going to use the Pythagorean's theorem in order to find this segment. And then using the fact that these two segments are equal to each other, I know that B is the midpoint of segment AC. So once I find this length, I'm going to call it X. We would just double it to find the length of AC. So X squared plus 6 squared equals 10 squared. So X squared plus 36 equals 100. When we subtract 36 from both sides, X squared is 64. And that means X is 8. Therefore, the length of AC is 2 times 8, which is 16 inches. In Explain 3 of this lesson, We have some more properties of perpendicular lines. First, we have this symbol representing perpendicular. So anytime you see this kind of upside down capital T, that means that two things are perpendicular. So I could be saying L is perpendicular to M, or line XY is perpendicular to segment AB. So in example 3, part A, we are proving that if two lines intersect to form one right angle, then they are perpendicular and they intersect to form four right angles. So basically, if two lines intersect to form one right angle, then all four of those angles formed by the intersecting lines will be right angles, and we can use the definition to say that the lines are perpendicular. And so they go through this proof. So we always, well, 99% of the time anyway, we start with our given, which is what they started with here. And they said that angle 1 and 2 being a linear pair is given. I would like to parenthetically add that is from the diagram. And then because the angles form a linear pair, I know that they're supplementary because of the linear pair theorem. Because these angles are supplementary, I know that they add up to 180 because that's the definition of supplementary angles. And then back here, we knew that angle 1 was 90 degrees, so that's why we see that 90 degrees has been substituted in for angle 1. Subtracting the 90 from both sides, I have that the measure of angle 2 equals 90. And the measure of angle 2 is going to equal the measure of angle 4. Notice in the diagram that they're vertical angles, so that's the vertical angle theorem. So that means that the measure of angle 4 is also 90 degrees by the substitution property. Angles 1 and 3 are also going to be equal to each other. They are vertical angles, vertical angle theorem. And then finally, substitution property one more time tells us that angle 3 also is a 90-degree angle. In the theorem that we're trying to prove in part B, we're trying to prove that if two lines intersect to form a linear pair of congruent angles, then the lines have to be perpendicular. So here I have L and M intersecting in such a manner that angle 1 is equal to angle 2. So by the diagram, I know that angle 1 and angle 2 form a linear pair. So angle 1 and angle 2 are supplementary by the linear pair theorem. By the definition of supplementary angles, I know that the measure of angle 1 plus the measure of angle 2 equals 180. It is also given that the measure of angle 1 equals the measure of angle 2. So I can take that angle 1 and put it in place of angle 2 using the substitution property. Adding these two things together gives me that 2 times the measure of angle 1 will equal 180. And therefore angle 1 will equal 90 degrees by the division property. Therefore, angle 1 is a right angle and L is perpendicular to M by the definition of perpendicular lines. In this reflect question, they're asking us to state the converse of the theorem in part B. Remember that when we take the converse of a statement, we're just flipping the statement around. So in this statement, the then of my statement is the lines are perpendicular, so that means that's going to be my if. So this statement will be if two lines are perpendicular, then they form a linear pair of angles with equal measures. And it is true. In this your turn, I've got a bunch of parallel lines. I've got B parallel to D, I've got C parallel to E, and I've got A as a transversal to both pairs. Angle 1 is given to me as 50 degrees. Angle 5 is given to me as 90 degrees, and I'm asked to use all this information to find the measure of angle 4. Okay, Well, angle 1 and angle 2 are corresponding angles. So I know that they're equal to each other. I know that angle 2 is equal to angle 3 by the vertical angle theorem. Right, so I know this is 50. I know, therefore, this is 50. And notice that angle 4 plus the measure of angle 3 plus the measure of angle 5 has to equal 180 degrees. I don't want to say linear pair theorem because pair implies that there's only two angles. But I could say that it's a combination of linear pair theorem and angle addition postulate. Okay, so that means that the measure of angle 4 plus 50 plus 90 has to equal 180 degrees because of substitution. And when I combine my like terms, I've got 140 that I'm then going to subtract from 180, and the measure of angle 4 is therefore 40 degrees by subtraction. In this last elaborate question that I want to talk about, it says, explain how the converse of the perpendicular bisector theorem justifies this construction of a perpendicular bisector of a segment. Well, let's go back and look. The converse of the perpendicular bisector theorem said that if a point is equidistant from the endpoints of the segment, then the point lies on the perpendicular bisector of the segment. So when this construction was done, what was found was that all of the points on this arc are the same distance from B as they are from A. So the place at which they intersected were C and D, which means C and D have to be on the perpendicular bisector. So when I connect those two dots, that line containing them is the perpendicular bisector. So by construction, C and D are equidistant from A and B. So the line containing them must be